An introduction to Legendre's chi function. So basically in my previous video I talked about the reflection formula of polylogarithm function. Yeah, which was something like this. This fraction by 2, this is equals to 2 to the power minus s, and then Legendre's s of x square. Yeah. Now in this video, like I've thought of talking a similar formula but with a negative sign over here, and this is in fact the definition of Legendre's chi function as well. Yeah. Now this thing over here, we are going to prove this thing, like how this comes. Yeah. And after the proof, we will also see an integral that involves Legendre's chi function. Okay. Now for the proof, you need to know about their definitions. Basically, a polylogarithm function for g is defined as sum going from n equals to 1 to infinity g to the power n by n to the power s. And Legendre's chi function for z is defined as sum going from n equals to 1 to infinity g to the power 2n minus 1 by 2n minus 1 to the power s. Yeah. Now for some of you it might have been obvious from the definition itself, like why should this be true, but if it has not, don't worry, we will solve it together. So basically we have this expression on the left hand side. Yeah. And we have to prove this as Legendre's chi function. Now first of all, let's use the definitions. 1 by 2 sum going from n equals to 1 to infinity x to the power n by n to the power s. Yeah. And what I can do is plug my charger. Just a second. Okay. Now it's fine. Now since both of them are going from n equals to 1 to infinity, minus, for the second one we will have minus x to the power n by, this is n to the power s actually. Yeah. Okay. Now let's see like how does this sum go. If n is an even power, we actually have x to the power n, let's say 2n by 2n to the power s minus x to the power 2n by 2n to the power s. Yeah. Now if it's even power, minus x to the power 2n will just be same as x to the power 2n itself. Yeah. So you can see that these both of the terms cancel out if x is an even power. But if x is an odd power, we have minus of, the minus also comes out, and we have x to the power 2n minus 1. So you can see that those two are actually added when we have an odd power. So that's why in odd powers we will have 2 times x to the power 2n minus 1 by 2n minus 1 to the power s. Yeah. Now if we are clear about that, now we know that this sum is only including the odd powers and get cancelled at even power. So that's why we can write this as 2 times x to the power 2n minus 1 by 2n minus 1 to the power s, and the 2 cancels out. That's why we have sum going from n equals to 1 to infinity x to the power 2n minus 1 by 2n minus 1 to the power s, which is the Legendre's chi function. Yeah. Okay. Now after we have derived this expression, let us go into an integral that involves Legendre's chi function. Yeah. Let's solve this integral. Integral from 0 to alpha, integral from 0 to beta of 1 by 1 minus x square y square dx dy. Yeah. Now since in the world of x, y is just a constant, so this is 1 minus g square form. So the integral is in standard 1 by 2a ln of 1 plus g by 1 minus g. Yeah, and a is just 1 over here, so that's 2 times 1 only. And since y is a constant in front of x, yeah, this is x all square, so we have to write 1 by y as well. This is going from 0 to beta per dy. Integral from 0 to alpha, 1 by 2. Now we have substitute x as beta, so we have ln of 1 plus beta y minus 1 minus beta y, sorry, by 1 minus beta y, minus at 0, this is ln 1 by 1, so that's just ln 1 is 0, and then times 1 by y dy. Now we have this integral. Now for this integral we can first let g as beta y, yeah, and then dz by beta equals to y. So we have integral going from 0 to alpha beta 1 by 2. Now this will be ln of 1 plus g minus ln of 1 minus g, yeah, and then y will be 1 by g by b, yeah, and then dy will be dz by b. Now this beta will be cancelling each other out, so we were left with this kind of nice integral, which I will rearrange in the following way: minus ln of 1 minus g by g minus of minus ln of 1 minus minus g by g, okay, and then dg. Now why have I rearranged in this way? This is same, yeah, but why did I make this manipulation? So basically indefinite integral of minus ln of 1 minus g by g dz, this is actually equals to li2 of g, yeah, derivation is over here. Now the indefinite integrals are li2 of g minus li2 of minus g, yeah, here's minus g. Now this is from 0 to alpha beta, yeah. Now this is needs to be evaluated at both the limits. Yep. li2 of alpha beta minus li2 of minus alpha beta, and then at the other limit we have li2 of 0 minus li2 of 0, so both of them are 0 in fact, because we know that li2 of 0 is just sum from n equals to 1 to infinity g to the power n by n to the power s. Now if substitute g as 0, this will be just 0 to the power n, so that's 0. And even if those were not 0, still both of them would have cancelled each other out, so 0. Now we have the definition of Legendre's chi function, yeah, li2 of alpha beta minus li2 of minus alpha beta by 2, and we know that this is just the Legendre's chi function for base 2 of alpha beta. So what a neat answer. It's not a neat answer though, because this is an like ridiculous sum, yeah, but just that because we defined the sum as the Legendre's chi function, so we get a neat answer. But if there wasn't that definition, then it would have been some ridiculous sums. Okay, we have proved this expression. Hope you enjoyed the video. Hope you are now introduced to Legendre's chi function. Look forward to seeing in the upcoming videos too.